Skylights in Riga. You have seen I have enhanced a little bit the title of my talk because I saw this is a theoretical institute here, and even Edward Witten will come next week, so I couldn't imagine to present only pictures of buildings and machines, so I did also add some theoretical point at the end of my talk. So let me start with a funny sentence here I found recently in a paper by Eugene Parker. His first paper was rejected by the editor of Astrophysical Journal, and he said, anyone who knows anything about astrophysics knows that magnetic fields have nothing to do with this. This was a common wisdom in '51, and I think this has recently changed. Now we know that magnetic fields do play a big role in the cosmos. They are on one side produced by velocity, by the dynamo effect, but on the other side they are very, very active in cosmic structure formation by virtue of the magnetorotational instability, by virtue of the Taylor instability. And reality might even be much more complex. There are dynamos of a higher order, so to say, the MRI dynamo, the Taylor-Sproyd dynamo for stars. So there is a slew of different mechanisms where V and B are connected, and I would like to call it the yin and yang of the cosmical astrophysical MHD. So still a little bit of motivation. We know the dynamo effect, we have a magnetic field, and then we have some flow, preferable a helical velocity. This gives an electrical current, and this electrical current reproduces the magnetic field, and if this happens, this gives the dynamo. The MRI, to take this example here, is very roughly, you have an accretion disk with different orbits of different mass elements, which would be stable in the hydrodynamic case, but the magnetic field acts a little bit like a spring, so it couples different elements at different orbits, and so it can lead to exchange of angular momentum and to turbulence at the end of the day. So, of course, dynamo is important for planets, for stars, even for whole galaxies. The MRI plays a key role for destabilization of accretion disks around protostars, around black holes. There is a nice new big book by Günter Rüdiger, Kitschatinov, and Hollerbach here. And what you see here is a funny cover picture for this book. This is not a star or accretion disk, but this is an experiment. And why is that? Because the last 15 years have seen a lot of experiments, and François has presented one of the most important ones on the dynamo. So we had the Riga, the Karlsruhe experiment in '99, the Cadarache experiment starting in 2006. We had a few experiments on the magnetorotational and related experiments, and I will show some slides about our PROMISE experiment in Rossendorf. With the DRESDYN project, we would like to continue this line of research with different aspects. So DRESDYN is, in the first instance, a platform for a variety of geo and astrophysics experiments, but also for other liquid metal experiments related to energy-related technologies. I will focus today a little bit on our precession-driven dynamo experiment, on the preparations of this. I will focus on the magnetorotational and the Taylor instability, a little bit coming to liquid metal batteries, which have to do with the Taylor instability here. I will completely skip measuring techniques and thermohydraulics of sodium fast reactors, which is also a part of DRESDYN. So DRESDYN is mainly a new building with a new experimental hall. Here is a rendering of the architect of the hall and the inside. And I'm very happy and proud to present you now the real status of the experiments. This took us some 4 years in preparations, and I'm very happy. It was an exhausting story to make all of this building here. You have a look here into, and what you see here, this red and yellow ones, this is the containment for the precession-driven dynamo. I will go into the details in a minute. The general scheme is, so in the containment we will have the precession-driven dynamo. Here will be a large experiment on MRI and Taylor instability in a combined way. We will have a liquid metal battery stand. We will have some stands for sodium fast reactor related research and so on. I come now to the dynamos, and I simply would like to remind you on 3 slides on the Riga dynamo, which became operative in November '99. Here's one picture from July 2010. So you have 3 concentric cylinders with a flow driven by a propeller. It took us years to optimize the flow, to maximize the helicity, to have as low as possible critical RM. Here is the simulated magnetic eigenfield, which looks a little bit like a DNS in biology, a nicely helical field. And here you see one of the experiments. We drive on the propeller here to some 2000 RPM, and what we get then is a nice self-excitation over many, many decades, and with a saturation level of the magnetic field, which depends on the propeller rotation rate. So in hindsight, we can say that all the predictions for the growth rates and the frequencies, both in the kinematic but also in the saturated regime, were to some 5, 10, or 15% more or less accurate. And the reason for this is that the Riga dynamo has a turbulence level of not more than 10%. So you can really take a laminar description in the sense of the Ponomarenko dynamo, and this does a quite good job here. Some of you might be interested in the present status of the Riga experiment. In 2010, we had a big problem. You see here a big effect. This buckle, this indentation here, arose from some overpressure in some of the cylinders. So this was a sort of accident. Nothing else happened, but this looks not very nice for an experimental dynamo. We have now reinforced this thing here. We will do also some changes of the post-propeller vanes in order to look possibly for some interesting saturation effects. This will, the Riga dynamo is reassembled this year. I hope that we can have next experiments in the next year. But now let me come to the very DRESDYN project. Why is precession interesting? There are several reasons. Of course, the common wisdom is that we have buoyancy in the Earth, which drives the flow, and then you have Coriolis force, which makes some sort of Busse-Rolls. There are some complementary theories based on precession, and I'm always impressed by this figure here, which was given by Consolini and De Michelis. If you take the probability density of your interreversal times from the Candy-Kent data set, you find some very nice maxima at n times 95 kiloyears. In 95 kiloyears, this is exactly the Milankovitch cycle of the Earth's orbit eccentricity. So this is one of the Earth orbit variations. Precession might be another one. And this means that Earth orbit changes might have an influence on the geodynamo, maybe not driving it exclusively, but at least influencing it or possibly triggering some reversals here. There are some more discussions on the lunar dynamo in terms of precession or impacts by Dwyer and Lebar. There is some evidence for an ancient core dynamo in the asteroid Vesta. There is a science paper here. So precession, mechanical stirrings, forcing are quite interesting now, and we would like to go a little bit into this direction. What we are aiming up is I call it now the hell machine, because it's a real terrible thing from the technical point of view. We are aiming at a precession-driven flow experiment with a diameter of 2 meters, a height of 2 meters, so aspect ratio 1. We aim at a cylinder rotation of 10 hertz and a turntable rotation of 1 hertz. This gives us a magnetic Reynolds number of 700. The big problem here is a huge gyroscopic torque, which amounts to something like 8 million Newton meters, and you have to have a very, very strong basement to bear that. Concerning dynamos, there was a strong motivation by the paper by Caroline No and Jacques Léorat, who predicted something like a critical RM of 700. We asked them to modify it also boundary conditions. So with some copper walls, it seemed to be possible to go down to 500. This was the status a couple of years ago. Now it appears if you go down with a PM, the predictions become less optimistic, so we do not really know whether we will have a dynamo here. There is some promising result of André Giesecke I will show in a minute. So here is the present status of the design. We are very close to technical clarity. For the main vessel, which is this 2 meters times 2 meter here, we have some conical end pieces designed for hosting some bellows for temperature compensation here. So all this will be installed in a big frame. We will have the possibility to tilt everything by 45 degrees to look for different parameters. All this machine will be installed in this, as I have shown, in this containment here. The tanks for a total 12 cubic meters of sodium are here, and then it will be filled and can pour down here. So this is the present status of the design. I show you a few funny details. We had some, so to speak, fundamental problems due to the huge gyroscopic torque. So we had to make a very, very solid ferroconcrete basement, the construction of which you see here. And for this, we had to drill 7 big holes into the bedrock. And this was the status in July, you see it here. And now you see the inner side of the containment with the tripod seen here. And this is the inner side of the containment. The fluid dynamics of precession is quite interesting, and we were really triggered and persuaded by Jacques Léorat, who did already a very nice experiment in the experiments in the ARTER facility in Paris-Meudon. Essentially, you have 3 regimes when your precession ratio, so turntable rotation to cylinder rotation, is quite small, 0.1. You have a more or less laminar flow with only the forced m=1 Kelvin mode. Then there is a regime where you get a little bit nonlinear, you get cyclonic regimes. This is a picture from Muhali et al. And above approximately 0.07, you enter suddenly a completely turbulent regime where all the modes are there. And yeah, in principle, we have the 3 regimes. We have done our own water mock-up in Dresden, which looks like this. Here we can also change the angle of the precession. In principle, it's also length to diameter 1 to 1. Here we have Reynolds numbers 2 millions, and the size compared to the large machine is 1 to 6, the size scale here. So we did a lot of experiments. We could also identify the 3 regimes. Here are some numerical values. What is very interesting in this water experiment is that this transition from laminar to turbulent is very hysteretic. It's a subcritical transition. And what you see here, this is the electric power of the driving motor. You see you go up from the laminar regime to the turbulent regime, and you come up at a little bit lower precession ratio, depending somehow on the angle of precession. So this is a clear hysteresis effect. And I'm very happy that Johan Hérault was with us for 1 year, and he did a very good work in analyzing this transition. And there is a physics of fluids paper submitted by him showing that this coming back from the turbulent regime might have the character of some super transient behavior of the mean waiting times. All this is not completely clear and very hard to do experimentally, but I simply want to say it's an interesting result even for the hydrodynamics here in this experiment. On the numerical side, André Giesecke did a good job in the last months or so in looking for different M modes, so the different Kelvin modes which are excited in precession. So what was known before and done by several people, Chang and so on, that you have the forced m=1 Kelvin mode. This goes like this. What was not seen in the experiment up to now is the appearance of the higher M modes, the higher Kelvin modes, which are somehow triggered by the m=1 modes. And this has been shown now by André Giesecke. He changed the aspect ratio of the cylinder, and he got quite different ratios of the higher M modes from M2 to M7. I think this is a very, very nice paper which is in preparation. And here you see the numerical structure of those M=2, 3, 4, 5, 6 modes which appear in different regimes. And what we are starting now is to do dynamo simulations based on those higher M modes. And they are quite promising, but we are not at the end of this one. I stop here with the dynamo and enter now the business of magnetorotational and Taylor instability. Most of you might know that magnetorotational instability is very, very important in astrophysics, but it traces back to a paper by Wellichow in '59. And Wellichow had shown, not for an accretion disk, but for magnetized Taylor-Couette flow is that you have in principle three regimes. If your inner rotation is very, very fast compared to the outer one, so that your angular momentum is decreasing outward, then it is really unstable, so it is stable from the hydrodynamic point of view. If your outer rotation is faster than the inner one, in terms of the angular velocity, then it should be always stable. And the interesting regime is between these two lines here, the Velisov-Chandrasekhar line and the Rayleigh line, where the angular velocity is still decreasing, but the angular momentum is increasing. This is the most interesting part. And here is where the MRI lives. And Kepler rotation applies directly to this regime. The citation history of MRI is quite interesting. So the paper of Velisov, this guy here, from 1959, was cited 2 times in 30 years, and then it rocketed a little bit, and then it rocketed in 91. In 91 was a famous Balbus and Hawley paper, who applied MRI to the astrophysics contacts to accretion disk. And here you see the citations of Balbus and Hawley, 2000 something. They got the Shaw Prize 2 years ago. But this is quite funny. Silence over 30 years. Anyway. Okay. Okay. What those people did is standard MRI. Standard MRI means you have a rotating flow and you apply a vertical magnetic field to this. This regime is governed by the magnetic Reynolds number and the Lundquist number. Both must be in the order of 1 or larger. And of course, some people dream to build this an experiment. There have been, and there are still efforts in Maryland and Princeton, but it's very hard to achieve those large Lundquist and magnetic Reynolds numbers. All the more, it came as a big surprise when Hollerbach and Rüdiger had a PRL paper in 2005, where they checked what happens if we add to the B set some B phi. And they detected that then the scaling completely changes. So the relevant parameters are not anymore Rm and Lundquist, but Reynolds and Hartmann. This gives you a completely different scaling. And this enables you, as a liquid metal guy, to make a quite easy experiment. And we did exactly this one. And this is our Potsdam-Rossendorf magnetic instability experiment, or PROMISE. A certain drawback is that it works for some steepness of the flow, but it does not work for flows as shallow as the Keplerian one. And when I first met Steve Balbus and I told him about this, he said, no interest in this because it's not working for Kepler flows. It's a little bit below, but I come back to this point in a few minutes. So we did our PROMISE experiment, which is a Taylor-Couette experiment, relatively small like this. We apply to the Taylor-Couette experiments 2 fields. The yellow coil gives you the B set, and this rod in the middle gives you the B phi. And here is one of the results if we have switched on some B set by this coil here, and now we crank up the B phi by this rod here. You see, this is ultrasonic measurements done here. Until 4,000 amps, you see nothing, and at 5,000, 6,000 amps, you suddenly get the helical MRI, as we call it now, in the form of a traveling wave which is traveling upward. So this was a result from 2006. It has been improved by some experiment now. I think we can say helical MRI is quite safely explored and we know where we are. What we have done in the last years is the following effect. Imagine now that you have a helical field and you go down with a B set to 0. So then you end up with a purely B phi. And there was a paper by Hollerbach, Tilak, and Rüdiger, also in PRL of 2010, who showed that then what you get is not anymore an axisymmetric MRI, but a non-axisymmetric one. And we call it, for some reason, azimuthal MRI or EMRI. And for doing this, so the 4 kiloamps which you have seen before, or 6 kiloamps, are not enough. You must go to 10 kiloamps at the central current. And in order to be on the safe side, it's always good for experimentalists to have a factor 2. We have decided to take one of the power supplies here for 20 kiloamps. And I would like to note that the field that we get here is not exactly a pure B phi. You see here are some LEDs going to this, and those LEDs lead to the fact that you have a little symmetry breaking of your B phi by some 5%, but this turns out to be quite important. Here are some results. Here is a simulation by Vladimir Galindo, what the AMRI would look like if the B phi were completely symmetric. And there is a certain symmetry breaking in the two hemispheres. You have a sort of butterfly diagram, so to speak, going down here, going up here. And now what happens if you add a little bit, some 5% of asymmetry of your B? It's not very much. You get a restoration of your symmetry here. So you get interpenetrating downward and upward traveling waves. This is a simulation, and here's a measurement. And they look quite similar. And in this PRL paper with Martin Sallmayer, we have shown a quite reasonable correspondence of the numerics with the predictions. Oh, sorry, with the measurements. Yet we want to have some more symmetric field, and recently we will, or in this week in principle, we changed the geometry a little bit by driving the current back in such a pentagon shape so that we can have a better symmetry of the B phi. I come now to the Taylor instability. So AMRI is a shear-driven instability which is catalyzed by a B phi. Taylor instability is an instability which is driven by the current. It taps into the energy of the current. So it doesn't need any rotation at all. And Taylor instability has been discussed as one in the context of the Taylor-Sproit dynamo. I'll come to this in a minute. It has been discussed for breaking of neutron stars and also for the structure formation in cosmic jets. We did 3 years ago an experiment on the Taylor instability. So we drive a current through a liquid metal, a most simple experiment. And the critical number here is the Hartmann number. It should be something like 21. And 21 for a gallium-indium tin experiment means 3,000 amps. And what we have seen here is, I'm not really happy with this experiment, but we see some evidence, both for the growth rate and the perturbation of the measured magnetic field here, that this corresponds really to the Taylor instability. I'm not very happy with the experiment, but there is some indication that it's really the Taylor instabilities that we have seen. I make a little break here, going back from astrophysics to earthly applications. We notice that Taylor instability might be important for some liquid metal batteries, which are presently heavily discussed as possible storages for renewable energies. Liquid metal batteries, it's a detail here, might consist of some sodium here, some molten salt, and some bismuth at the bottom. And this is a very nice and extremely cheap battery. That's why people are discussing that. The point is only, if you build it large and you have 10,000 amps in sodium, you will, in any case, make a very strong Taylor instability here. This might drive a flow, and it might destroy here the molten salt layer. That's why, here's one picture of our first liquid metal battery. It's really working, but it's not so important here. We were looking now for how can we simulate it in numerics. We made a new code based on the OpenFOAM library. We added the Poisson equation for phi, and we added Biot-Savart for the induced magnetic field, which is important here. So this gives you such a structure, and this is a paper by Norbert Neber in NGP. And this code is really capable to nicely simulate Taylor instability at very, very small magnetic Prandtl numbers for liquid metals, which is not so easy for other codes. So we see, for example, the growth rates over the current in nice agreement with our measurements here. I skip this, but I would like to draw your attention to two things. If you have such a battery, you might ask, how can you prevent the Taylor instability from occurring? And there are two options. And one of them is take a current and guided through the middle of your battery, and this will stabilize or will work against the Taylor instability. The second one takes the same current, make a Helmholtz-like coil, and produce some B set. So either you drive a current back or you produce a B set. I show this because these two mechanisms which work against the Taylor instability have some background in the natural saturation mechanism of the Taylor instability itself. Because if you have a Taylor instability, it will produce some m equal 1 mode, and this m equal 1 mode will give you an alpha effect, perhaps, I come back to this, and a beta effect. So the beta effect means this is an increased resistivity which somehow corresponds to a countercurrent. This is our picture of the current through the middle. The alpha effect drives the current like this and produces a B set. So both mechanisms lead to a saturation of the Taylor instability, and you can use those mechanisms to stabilize a battery. Let me come now a little bit to the alpha effect. Both mechanisms have been discussed in plasma physics for a long time. So, for example, the B set corresponds to the Kruskal-Shafranov condition of plasma physics. The alpha effect. This is very, very important for the Taylor-Sproyd dynamo model. Taylor-Sproyd dynamo model means you have a B phi which is wound up by the differential rotation in a star. But where is the alpha effect coming from? This is a big question here. And the point is the Taylor instability able to produce a dynamo effect? For large PM, Bonanno and Axel Brandenburg had produced a very, very nice model with a simple differential equation system here for the energy and the helicity, and they found this nice diagram, and they detected spontaneous symmetry breaking which corresponds to a finite alpha effect. But what happens now for small PM? Small PM might even be the tachocline, 10 up to minus 2, or even smaller. But it definitely corresponds to liquid metals. What happens here? And what we observed in our numerics is the following. So Taylor instability grows up, makes the m equal 1 mode. So this is U is increasing exponentially. And you get some spontaneous symmetry breaking for alpha. You get some alpha. But at the end of the day, in the saturation, it goes to 0. So symmetry is restored. Here is beta. Beta effect is there. The point is only for liquid metals or solar tachocline maybe, both the alpha effect and the beta effect are not strong enough to saturate the Taylor instability. In our case, we have a quite different, it's a purely hydrodynamical saturation mechanism. We get a m equals 0 mode from m equal 1, we get a m equal 2 mode, and those two modes saturate the Taylor instability. Yet, what about the alpha effect? The last picture was for Hartmann 40, I guess. Now we go to Hartmann 70. Here's again the exponential increase of U, and the black one is the alpha effect. So you have a symmetry breaking in the kinematic phase, and then it settles to 0. But what you observe here is a sort of helicity wave. So alpha makes a wavy structure here, which is quite funny, and it was unexpected. So if we, sorry for the very complicated picture, if we go to Hartmann 100 here, alpha the oscillation not only decays, but stays here and oscillates. And this is, now I come to the most speculative part of my talk, and I hope you don't kill me for this one. You might have heard that in the last 5 years or so, there is some speculation that planetary motion might influence the solar dynamo. When I heard it for the first time, I thought, this is completely bullshit. But there is some evidence, which is even disputed, I know, but imagine the evidence would be there. What then, you might ask yourself, what is then a dynamo model which could work on the basis of, or which could allow to have some influence of planets? And one of the candidates, which I see here, is a sort of Taylor-Sproyd dynamo. So you have always your B phi, which you get for free by differential rotation. The question is now, what about alpha? We have seen alpha oscillations, and what I show you here is a sort of parametric resonance. What we did, we emulated planetary torques by a m equal to viscosity wave or oscillation, which is going around. And what we saw, we got a frequency doubling. So if we have, first of all, you have a synchronization with this viscosity wave. You have an entrainment. You have entrainment, so to say. And what you get here is half of the period. This means a frequency doubling for your alpha effect. Now take the famous Venus-Earth-Jupiter conjunction, which is 4477 years. And take half of this. This is 22 years. I leave the conclusions for you.
5 minutes.
5 minutes, very good. So I come now to a little bit of theory. I talked about Amri and Taylor instability. Together with Oleg Kirillov, we worked a little bit on the theory connecting both things. Because when you are in the tachocline, you do not know what is your B phi. What is the radial structure of B phi? So we took Navier-Stokes, we took induction, we defined viscous resistive Alfvén frequencies. We have some additional numbers here. We defined two important numbers. The Rossby number, which is a hydrodynamic Rossby number, which gives you the steepness of your omega. And an equivalent, the magnetic Rossby number, which gives you the steepness of your azimuthal Alfvén speed. And then you can take Bilhart's criterion. You have this secular equation. This is a very long paper in GFM recently by Kirillov and us. And here was a PRL paper also recently. And what we have observed here is if you take Rossby here and magnetic Rossby here, what was known until recently was what we call the lower Leo limit, tracing back to a paper by the Princeton group, Leo, who analyzed the helical MRI, and they found helical MRI does not work for Kepler, but only for a little bit steeper profiles. So Rossby number not 0.75, but 0.828. In the same paper, those guys mentioned there is also an upper Leo limit. I come back to this in a minute. Upper Leo limit means you have a positive Rossby number, positive shear. This should become unstable. Very, very strange. I come back to this. In this paper here, we showed that the two Leo limits are just the endpoints of one common curve in the Rossby, magnetic Rossby plane, which connects both. And this means you can reach Kepler even when you have a little bit current in the fluid, if you have a little bit contribution from the Taylor instability. I find this quite remarkable here. Maybe I skipped one point. You might have a look in the papers. In the context of this, we have seen that the old Chandrasekhar theorem, that flows whose V phi is the same as the B phi in Alfvén speeds is stable, is not true. You have a dissipative instability here, so Chandrasekhar solution is not stable, but I skip this here. I skip also this one. Just let me come now to the experiment. Let me come back to DRESDYN. We want to build a large experiment, and which will allow us to hunt also for the standard MRI. So we are aiming at looking for standard MRI, so we will have a magnetic Reynolds number of 40 and a Lundquist number of 8. But in addition to this, we will start in the well-known regime of helical MRI, of azimuthal MRI, so that we can trace the instabilities to the regime of standard MRI. And this is the present status of the design of this experiment. It's as large as a GdR Dynamo, so it's also a huge machine here. Some technical details. 1 minute? 1 minute. I showed you already this picture, the old Velichov picture. Always unstable, MRI unstable, always stable. But is it so? Our flows, which are with positive shears, are always stable. And I showed you already, the answer was already given by Wei Liu, that there should be a positive Rossby number beyond which a flow can be destabilized by helical magnetic fields. Now, with Oleg Kirillov, we were looking on this in more detail for a purely azimuthal magnetic field. And we found the following. This is not for magnetic Rossby -1, but for zeros. This is still the Taylor instability for a small gap. So you have a critical Hartmann of 2,500. And this is the first remarkable effect. If you switch on some positive shear, the instability is enhanced, which does not goes without saying. And the same was done by Günter Rödiger in a recent archive paper with a one-dimensional Taylor-Coët setup. So look at those curves. This is WKB. This is a one-dimensional Taylor-Coët, and these are more or less exactly the same curves. So Oleg Kirillov, he is a big fan of Maple, and he took all the Bilhart's criterion, let it work by Maple, and then he arrived at this red formula here. This formula works for PM equals 0, and this is in this paper here. It connects the critical Reynolds number with the Hartmann number, the magnetic Rossby, and the normal Rossby. It's a closed formula. And we can apply now for PM0 this closed formula, and we can go over now from this picture, which you have seen a minute before, here, and now we go to a more and more negative Rossby number, ending up, magnetic Rossby number, ending up at this point, which is AMRI. And what you see here, this is a nice transition between Taylor and AMRI. And this is my last slide here. I indeed believe, here's a Reynolds number, here's a Hartmann number, here are the Rossby numbers. I indeed believe that positive shears can be destabilized by purely B phi, which is remarkable, I guess. And we have submitted a paper here. You can look. The point is only, to do it in experiment, you need a small gap, 0.9 approximately. And you need a current of 80,000 amps, even for sodium. And unfortunately, this goes beyond our plans for DRESDYN, so I do not know if we can do it later. At least I would like to stop here, and I would like to thank you for your attention.
So, questions, comments? Between geomagnetic reverse and peaks.
Yes.
And you mentioned that in your experiments, laboratory experiments also, you are trying to see the, I think, effect of precession. So what you are doing in your laboratory experiment, is that very analogous to Milankovic cycle, or can you make a direct connection?
Not exactly. So what we will start with the pure precession. If we later can change maybe some angle or some precession ratios during the run, let's see. This is a big problem of technical safety and so on. For the moment, we would be happy to get a dynamo in the precession experiment at all. So let alone all the higher effects of of Milankovic cycles also. It would be a dream to do this, of course. Yeah.
So the recent prediction for the precision experiment, is that you set the fixed PM, or you say that?
Yeah, this is the computations by Caroline were at PM1 or close to it, and they were quite optimistic. And now she is going down, and critical RM is increasing. So, of course, there were the predictions by Andreas Tilgner, by Krause, which Krause, for example, in a cube, they all converged a little bit to this RM 600, 700. But this was all for PM1. So up to now, to be very honest, I do not know if this is a dynamo. Andre Giesecke does now the simulations with the higher M modes, which is quite interesting, also from the hydrodynamic point of view. But we are still working on their dynamo action. There is one, but how far we can go down, I do not know. To be very honest, this is the state.
Then if you draw RM as a function of the kinetic Reynolds number,
sorry?
If you plot critical magnetic Reynolds number as a function of kinetic Reynolds number PM,
Yeah.
what's the asymptotic?
I think Caroline doesn't have an asymptotic yet, so she's going a little bit down with PM, but it was a deteriorating effect, definitely.
Would you plan to have the opportunity to impose a strong field on the precession experiment?
We have also the central current, so we will start at normal Reynolds numbers, say 20,000, so we will have, hopefully, helical MRI, azimuthal MRI, and then we crank up Reynolds. And we would like to see what is going on with the modes. There is a monotonous, continuous transition between helical MRI and standard MRI. And then we will see how we can go. This is a little difference to the Princeton experiment. They don't have any B phi. So we hope that we can go to Reynolds 2 millions to see the standard MRI. But even on the way, it's not that we have something. And we will see how far we can go there. But of course, the dream is to enter the final regime with a pure B set. Let's see.
Okay, I see no further questions, so let's thank Frank.
Thank you.